So let's go ahead and talk about the scientific method. Now, in a sense, there's not really one scientific method. What I mean by that is the the method to figure out the ideal mail route is not going to be the same method used as a biologist trying to grow a sample in a lab. Really, it's more of a thought process. What we're kind of doing is we're trying to come up with hypotheses, things that we can test, making some observations and making some experiments. It's really the thought process that makes the scientific method. Now, here we kind of have the the 5 steps of the scientific thought process, or the scientific method, if you will. And really, it's a process for change. And what I mean by that is it's a process that can be repeated again and again and again until we figure out the answer to what we're trying to figure out. So first thing you want to do is recognize a question. So let's make a question right here. Suppose I have my car and my car won't start. So that's a question, a puzzle, or something that's unexplained. Then we have to make a hypothesis, and a hypothesis is a testable, underline that several times, testable educated guess. So for my car, let's just say that the problem is that the battery is dead. We're going to predict the consequences of the hypothesis. Okay, if I were to replace the battery or get a jump start, then my car will start. Of course, now we can go ahead and perform this experiment to test our prediction. If I swap out if I get a set of jumper cables, my car will start. So perform the experiment, get a buddy, get some jumper cables, and perform the experiment, and then formulate the simplest general rule that explains this. Okay, my car didn't start. So so the process for change, we kind of go all the way back up to the top, and we're back here with my same question, my car won't start. So let's go ahead and make a hypothesis, something that is testable. Well, maybe I shouldn't try to start my car with my house key. Maybe I should actually try, my car key. So predict the consequences. Okay, if I try to start my car with my car key, then my car will actually start. I can predict the consequence of that. Perform the experiment, try to start your car with your car key, and vroom, the car starts up. So formulate the simplest general rule. Okay, don't try to start your car with your house key. You definitely want to use your car key. So kind of a silly example, but a way to work our way through the scientific method and figure out answers to questions. So what I'd like for you to do right here is to pause it for a couple seconds and answer to yourself which one of these is a scientific hypothesis. Okay, good. Now that you've thought about this for a while, what we want to keep in mind is that a scientific hypothesis is testable. And can we send a man to the moon and see if it's made out of green cheese? Yes, we can. Are atomic nuclei the smallest particles in nature? Well, we can try to split one open. So this is definitely testable. We can get a copper penny. We can get a magnet. We can definitely test that, even though pennies aren't made of copper anymore. And we can get a cosmic ray gun and see if it'll penetrate the thickness of your textbook. So we can test this guy as well. So all of these guys are testable, therefore all are scientific hypotheses. Examples of things that are not would be there are things in this world that we will never discover, right? We can't really test that, so that's not a hypothesis. So as we think about the scientific method, let's just talk a little bit about the attitude that we should have as we work our way through it. Definitely is going to be an attitude of inquiry. We want to figure things out. We have to be willing to perform experiments, and we have to sometimes admit that we're wrong. We thought things behaved a certain way, but we did some tests, and it turns out that we weren't entirely right, and that's perfectly acceptable for a scientific attitude. Really, that's how we learn things. So what that means is scientists are expert at changing their minds. If you don't believe me, just ask my wife. Not as expert as politicians, but we won't go there. Scientists also have to be willing to accept everyone else's experimental findings. So as you do your labs, I have to say, well, you made your measurement and it is what it is. But we do have to go ahead and say, well, I don't really believe that, so we do have to test for things that don't make sense, and we definitely want to understand what's going on with the world around us. Now let's just get a little bit of science jargon out of the way. It turns out that if you have a hypothesis, a testable idea, and you test it, and you test it, and you test it, and everyone and their uncle tests it, and you know the limitations, it works all over the place, that hypothesis is very special. We actually call that a law or a principle. So we'll be talking about Newton's laws in the next couple of chapters, and these are hypotheses that have been tested by everyone and their uncle. There's also something called a theory, which is when we say, well, we have this large body of information, it's pretty well tested, we're pretty certain about certain aspects of it, but we can't really test it. An example of that would be something like the Big Bang Theory, which is something where we say, okay, well, we're pretty sure this is the way that things work, but can we go back and recreate it? No, we can't recreate it. So that's why this is a theory versus a law. Now, science and technology, sometimes they are used interchangeably, and in a lot of cases they can be, but they're actually a little bit different. Science is concerned with kind of gathering the information, figuring things out, organizing it, and things of that nature. And what technology does is it's not really so much interested in gathering and organizing, but actually saying, okay, well, we have all this knowledge, let's do some practical applications of this. So, science is concerned about, making circuits and stuff like that. Technology is saying, okay, well, the science is worried about, the circuits. Now let's take this circuit and build it into something useful like a smartphone. So let's kind of finish off the chapter by talking about the units that we're going to be using. We're going to be using the SI system, also known as the metric system. And when we talk about quantities such as length, mass, time, and temperature, we may be used to the English system where we're talking about feet, pounds, seconds, and degrees Fahrenheit. And this is the point where most professors get up on a soapbox and say that the US is one of the few people still using these units. I'm not one of those. I actually think English when I think about cutting boards and stuff like that. However, when we talk science, pretty much all scientists use these units right there, and these are the units that we'll be using in this classroom. So when I think science, I think SI. When I think real world, I think English. Now, the unit for length is going to be a meter, abbreviated by this lowercase m, and a meter is about 39 inches or about 3 foot. I'm going to be using a kilogram, where a pound is 2.2 kilograms for mass, by kind of the kg right here. Seconds is still the same, and temperature is going to be in Kelvin. I'll talk a lot more about the temperature unit as we get into thermodynamics. Now we can go ahead and put prefixes in front of these units. So let's just consider, for example, if we had something like 1,000 meters, then that's actually going to be 10 to the 3 meters, and sometimes it's a lot more convenient to write that as a more palpable number. And if you go ahead and you take a look at this guy right here, a kilo, it's going to be 10 to the 3, so we could replace this 10 to the 3rd by a k, and we could be talking about 1 kilometers versus 1,000 meters. So let's go ahead and get some practice with this. Suppose I had something that was maybe, let's say, 300 kilometers long, and I wanted to convert this into meters. And what I would kind of do is I kind of come over here and I say, aha, there's my kilo, and I know that that's going to be a factor of 10 to the 3rd. So what I know that is in 1 kilometer, there's going to be 10 to the 3rd meters. And essentially what I'm really doing is in this parentheses right here, I was essentially multiplying by 1 because these are equivalent. But what I can do is I can cancel this unit right here with that unit right here, and I end up with 300 times 10 to the 3rd meters, or 300, 1, 2, 3, so 300,000 meters. And you can pretty much do this with any prefixes. Pretty much in this class right here, you definitely want to know mega, kilo, centi, milli, and as we go into As we go into Physics 102, probably micro and nano are going to be the important ones. So make sure that you're able to go ahead and convert units between these various prefixes. Now you may be asking yourself, why are we using the SI system? It turns out it does make things quite a bit easier. If we were to take a look at water, for example, and we were to talk about 1 cubic centimeter of water, it turns out that's equal to 1 milliliter, which is equal to 1 gram. 1 liter of water is going to be 1,000 cubic centimeters, which is equal to 1 kilogram. So things in SI units are very typically related to each other by a factor of 10. For the backpackers in the world, we know that 1 gallon of water is going to be about 8.3 pounds, where a cubic inch of water is going to be 0.036 pounds. So life is not so good in English units. It is good in the SI world.